Good afternoon. My name is Tobias Fischer, and I will talk about gas geochemistry to advance understanding of geothermal processes. When we think about using gas geochemistry, we can think about using different techniques to understand either the source of the gases or the processes that are happening in the subsurface. On the left side, there's a summary of some of the techniques we use to understand gas source. And here, it focuses on helium-3-4 ratios. On the right side of the diagram, we can use ratios of gases to understand the processes that lead to these ratios. A recent study that we did in the East African Rift illustrates the power of looking at gas sources. On the left diagram, you see that there is a map that shows you the mantle CO2 emissions measured on the craton, the Tanzanian craton, up into the rift. We see that there's a clear distinction in terms of the CO2 that is emitted on the craton versus the rift. In the lower part of the diagram, shown here, the mantle CO2 flux is very, very low, 6 grams. In the northern part, right in the rift, the mantle CO2 flux is very high, an order of magnitude higher. So that tells you that over here in the northern part, we get significant amounts of CO2 from the mantle, whereas over here on the craton, we get essentially none. We can look at the carbon isotopes and the helium isotopes to further substantiate those findings. Those measurements are relatively easy to do. With a CO2 flux meter that we put on the ground, we can measure the flux of CO2 from those different soil areas. Another example of using this technology is shown here. This is a geothermal area in southwestern Utah in the United States. Here my student Kristen Rahili has done a very extensive grid of measuring CO2 fluxes. And what she has shown is that in areas to the northwest, we have very low CO2 emissions. Essentially, it's background flux. There is no contribution of any elevated CO2 flux. However, on the other side of this fault that's been mapped in here, we can see that there's elevated CO2 flux. It turns out that on the right side of that fault, we have a hydrothermal system that brings up fluids along the fault from depth. Whereas on the left side, we're essentially looking at background CO2 without any deeper CO2 contributions. So looking at CO2 emissions by using this simple technique is quite powerful in understanding where the fluids are and where they come up from depth to the surface. However, the rest of the talk, I really want to focus on process rather than source. Now, volcanic gases sample a mixture of volatiles that come from the magma and from the surface region. The surface region is influenced by rain and by, then as a result, a hydrothermal aquifer that affects the composition of these gases. So the magma emits gases, those gases move to the surface and interact with the hydrothermal system that has mainly a composition dominated by water, but also some other gases like CO2 and methane and so on. So complex reactions happen in this system. And when we try to understand the processes that are occurring, we can focus on a few of these gas species. So hydrothermal gases are low temperature gases. And here's an example table of hydrothermal gases. You see that the temperatures are all below boiling, essentially. Here, for example, is Papandayan in Indonesia. And we see that these gases are dominated by water, CO2, and in terms of sulfur species, by H2S. There's very little chlorine, there's essentially no fluorine, and there's some hydrogen, some methane. And if we go to the next slide here, we see that there's also very little CO, and we have certain ratios that determine whether we have air or air-saturated water or different carbon isotopes. So there's a lot of things we can measure and investigate when we look at hydrothermal gases. In order to understand these processes, we can focus on some key redox relationships in those gases. While we have this overwhelming compositional variety, we can focus on a few species that are helpful when we try to understand process. So some key redox relationships are shown here. Water going to hydrogen and oxygen, CO2 going to CO and oxygen, CO2 and water going to methane and oxygen. So those are some key reactions of the hydrogen and carbon gases. And for each of these, we can write an equation that involves the equilibrium constant. So in this case, we consider equilibrium in a single vapor phase. Then we can manipulate these relationships and we can solve for the fugacity of hydrogen, the fugacity of carbon monoxide, and the fugacity of methane, for example. And we can see that these fugacities are related to the equilibrium constant, again, of the reaction, and to the oxygen fugacity and the water fugacity in almost all of these reactions, you see. So the fact that we have redox relationships is really important. It determines what the gas composition is going to be that we will sample at the surface. And we can then use these kinds of relationships to make a diagram like this. And this is a very famous diagram. It's been around for a long, long time. And what it essentially shows you is the fugacity of these gas species depending on temperature. So temperature is high to the left, 300 degrees, 100 degrees on the right. And we see, for example, that the fugacity of water decreases as the temperature decreases, fugacity of CO2 decreases as the temperature decreases, fugacity of methane goes up, and hydrogen goes down. CO, for example, has a very low fugacity, and it also decreases with decreasing temperature. So this diagram is helpful to understand what the relative abundances of these gas species are in equilibrium. And there are two different lines here. One is Ligenbach's 1987 relationships in solid lines, and D'Amore and Panici's line in dashed lines. So slight differences in the distribution, but overall, this would be an equilibrium distribution for these types of gas species at different temperatures. However, in volcanic gas and geothermal gas geochemistry, we cannot determine the individual gases or the individual fugacities for fumarolic gases. So by fumarolic gases, I mean gases that come out of gas vents. So we can't really compare the figure that I just showed to use as a comparison of theoretical values to actual samples. Now we can get around this very easily, and this has been recognized by Gegenbach and co-workers by simply using gas ratios. And so through a lot of research and work, people have established some key gas ratios. And so what I show here are some of these key gas ratios, right? So the log X water to or hydrogen to water ratio is an important one, and it essentially relates to the fugacity through that relationship with the equilibrium constant. So in this diagram, we see that we have the relationship between hydrogen and water, CO and CO2, and methane CO2. So these three ratios are really key when we try to understand the processes that are happening at depth. And again, you notice here that I'm only showing hydrogen, carbon, and oxygen gases. Sulfur gases are not included in this assessment for simplicity. Now, when we utilize those relationships, we can make plots like this. And what you see here is a plot of the logarithmic relationship of hydrogen to water and CO2. And we can calculate these vapor lines and the liquid lines, and I'll show in the next diagram how that is done. And once you have that, then you can plot your data, because your data, your samples are analyzed for hydrogen and water contents and for CO2 contents, amongst all these other gas species that you might want to analyze for. And what you see then here is a number of data points from many different volcanoes all over the world. For example, we have Tambora here from Indonesia, right? And we can then plot it on this diagram. And you see that if some some data point plots right here on the vapor phase, then that implies that this gas originates from a vapor-dominated system at depth. And then the question becomes, well, what is the temperature of equilibrium at depth? And you can read that off of this diagram, right? So in this case, it would be about 150 degrees C. Now, if you have a sample that plots closer to the liquid line, for example, these I data points here, those are from Asia and Italy, then that implies that the origin, the source, and the process of that sample is a liquid-dominated system at depth somewhere. We don't know exactly where that liquid is, but we know it's there somewhere at depth. And that gas comes from the equilibrium with that liquid phase, and that liquid phase has a temperature of 300 degrees C. Now, any samples that plot in between those two are likely a mixture between a vapor and a liquid-dominated reservoir. So this analysis is really useful in understanding the processes as well as the source of those gases, and they give you an idea of where the high-temperature reservoir is and whether that reservoir is liquid or vapor-dominated. Now here, I just show how you can make such a plot. What you need to do is you have to have, for example, an equation like this that allows you to calculate the vapor log H2H2O with this equation. So it relates to temperature here in Kelvin, which you can easily convert to degrees C. And then you can make the plot here for different temperatures. So each temperature corresponds to a different hydrogen-water ratio. For the liquid part, it's a little bit more complicated, but essentially you will have to have the liquid-vapor distribution coefficient to compute the coexisting liquid. And those vapor-liquid distribution coefficients are available in the literature, so you can essentially calculate the liquid and the vapor relationships yourself make a diagram like this, and then you can simply plot your data points from your samples on this diagram to establish what your source and your process is at depth. So I've shown you how we can use CO2 flux and gas chemistry to establish where there are fluids coming from depths, what the temperatures are, what the source is in terms of liquid or vapor, and where most of the flux would be coming up. So these are methodologies that can be easily deployed by collecting samples in the field and doing some relatively straightforward analyses of these samples. Of course, we can extend those analyses to include isotopes and trace elements for even more detailed information on these geothermal and hydrothermal systems. Thank you.
Good afternoon, everyone. Thank you for the opportunity given to me. Today, I would like to share my paper about geothermal prospect review in the western part of Salak Volcano, West Java, Indonesia. First of all, I would like to thank Star Energy Geothermal Salak for granting permission to publish this work. Massive thanks to Pak Yudi and Pak Glenn as my supervisor, and also Ibu Suryantini for reviewing my paper and for your valuable feedbacks. The topics that I'm going to present is actually an ongoing study, so I really appreciate for any comments and feedbacks for my presentation. This is the outline of my presentation today. I will start with introduction, background and objectives, geology, geochemistry, geophysics, conceptual model, and conclusion. Star Energy Geothermal was established in 2003 as an independent national energy company whose operation bases are mainly in Indonesia. Currently, Star Energy Geothermal operates 3 major geothermal fields in Indonesia, namely Wayang Windu, Darajat, and Salak, with total capacity of 875 megawatts. The Salak geothermal field is currently the largest geothermal producer in Indonesia with an installed capacity of 377 megawatts. Commercial production at Salak commenced in 1994, and currently there are 6 power plants units. The location of study itself is at the western part of Salak Volcano, southern Bogor District, West Java Province, Indonesia. Gunung Salak, with elevation about 2200 meters, is a prominent stratovolcano located in the Quaternary volcanic front of the Sunda Arc in West Java. This slide shows the background and objectives of this study. The area of interest that we called as Kawah Ertankian is a vigorous fumarole area with numerous superheated and boiling steam fans, boiling acid sulfate hot springs, and large areas of acid altered ground. Extensive geological, geochemical, and geophysical surveys conducted in 1982 to 1983. However, none of current Star Energy resource management involved in Ertankian exploration. The objectives of this study is to revisit Ertankian field data and conduct thorough evaluation of geologic, geophysics, and geochemistry to provide alternative conceptual model and proposition of further study or future action item. From this topographic map, we can observe that there are several prominent eruption centers: the Gunung Salak itself, Gunung Gagak, Gunung Perbakti, and Gunung Halimun, and also Cianten caldera at the west part. The Salak volcano is the largest and most easterly cone in the Salak Perbakti Gagak volcanic massif as a product of late Pleistocene to recent stratocones, parasitic vents, and phreatic craters. The Perbakti Gagak range to the southwest is strongly eroded. Both areas in the northeast and southwest are sites of extensive hydrothermal activity. Intermittent volcanism occurred at Salak between 200,000 to 1 million years ago. In historic time, volcanic activity at Salak has been limited to a number of phreatic explosions occurring at the side vents on the flanks of the volcano. The summit area of Salak is characterized by two large bridge craters, one open to the northeast and another to southwest, which are associated with volcanic sector collapse events. And the westernmost crater was the source of large debris avalanche deposits, which extends over 10 kilometers from the summit. A late-stage dome built on the western crater rim as a result of the most recent activity. From this regional geology map, we can observe that there are two major volcanic products came from separated eruption source, the pre-Salak volcano and Salak volcanic products. Pre-Salak volcano consists of andesite lava of Gunung Menyan, old volcanic deposit at the southeast, andesite lava of Gunung Endut Perbakti, and lahar deposit at the northeast. The volcanic products itself consists of 4 episodes of lava flows from Salak volcano, pyroclastic airfall deposit, which consists of scoria and pumice, Gunung Sumbul lava flow, lava dome, several lahar deposit, and phreatic avalanche deposit in the northeast. This map shows closer look to the study area. And Kawah Ertankian is a vigorous fumarolic area, contains numerous superheated and boiling steam vents. Sulfur is deposited around many of the vents. The gas in fumarolic area relatively high NCG, above 4% weight, and high H2S, above 6% mole. Two dominant fracture trends are present in the area of interest and has a strike of northeast-southwest and northwest-southeast. These dominant fracture trends are also found in the commercial Salak geothermal field. The Salak Pelabuhan Ratu regional fault, which has trend of northeast-southwest, extends more than 7 kilometers south of Salak volcano. This is relatively parallel with the Salak volcano sector collapse wall. The northwest trending fractures intersect the northeast set in the vicinity of the Kawah Ertankian. This structural intersection may well have controlled the location of the Ertankian hydrothermal system. The northwest trending faults appear to channel shallow outflow and surface discharge from the hydrothermal reservoir and may also constitute boundaries of the deep reservoir. Another prominent alignment is the northwest-southeast trending Perbakti structure, an infer fault located between the Salak geothermal field in the west and the Ertankian geothermal prospect in the east that could have an important role for the Salak and Ertankian geothermal fields. The Ertankian hot springs has acid sulfate character and yields little information about the underlying hydrothermal system. The ternary plots show spring samples from Ertankian, zeta, beta, and gamma thermal manifestations. From chloride sulfate bicarbonate ternary indicates that the Ertankian spring is typical of sulfate, zeta is chloride, beta and gamma springs are mixed bicarbonate chloride waters. While from the ternary of natrium, potassium, and magnesium, it shows that all springs are immature, while zeta, that believed as the best representation of liquid level of the Salak geothermal system at surface, is the only one in partial equilibrium state. A significant aspect of the Ertankian fumarole chemistry is the stable isotope composition of steam condensate. The Ertankian steam contains much heavier hydrogen and oxygen than local meteoric water, indicating a significant non-meteoric component in the reservoir fluid. The presence of the non-meteoric component implies a strong flux of the component into geothermal reservoir relative to meteoric water influx during the historical life of the system. Possible origins of the thermal fluid are old formation water and or magmatic water. This slide shows the gas geochemistry of the Ertankian surface thermal manifestation. So majority of Ertankian gas is related with high temperature deep upflow as plotted in this part, while Zeta hot spring show a mixing line with air saturated water. And from this ternary plot, majority of Ertankian gas plotted in the H2SN member, while Zeta and CG reflects almost pure carbon dioxide as typical peripheral fluids. A geophysical survey was conducted in 1983 in the area of interest during the exploration. In this survey, magnetotelluric stations were distributed around the broader prospect area toward the east region of the prospect in the vicinity of Kawah Ertankian area. Although the survey was conducted with a wide coverage, a number of the magnetotelluric stations were not used because of the low signal-to-noise ratio and absence of a static shift correction on the data. In 2004, another MT survey coupled with time domain electromagnetic or TDEM measurement was conducted. However, the survey mainly concentrated in the Salak production area and did not give significant improvement to the data coverage in the eastern portion of the Ertankian prospect. An extensive area of low resistivity is distributed across most of Ertankian prospect area. Low resistivity zones are found around the Ertankian thermal manifestation complex and broaden to far northwestern Warm Spring in Beta and Gunung Perbakti in the southwest. These low resistivity zones can be due to several types of clay-rich deposits such as volcanic clastic clays, sedimentary basin clay deposits, or smectite argillic clay alteration overlying a geothermal system. Within the Ertankian prospect, the low resistivity layers that are near to and appear to be associated with surface thermal manifestations are believed to most likely represent the signature of a clay cap over a geothermal reservoir or outflow from a geothermal reservoir. A standard way to view the characteristics of the low resistivity layer is to contour the elevation of the base of conductor layer. In the case of Ertankian, the elevation of the base of less than 10 ohm meter layer was determined from the 1D MT models from each of the MT stations. The figure shows that the shallowest base of the conductor is observed in the area near the Ertankian fumarole and possibly extends to the northwest towards the alpha well or A-3 well area. Towards the south and southwest from Ertankian, a significant deepening of the base of the clay cap is observed. However, there is minimal information to describe the area east of Ertankian thermal area, as the latest empty stations were located west of the Ertankian prospect. In addition to the information from the base of the conductor, the total conductance map shows the highest value is in East Ertankian thermal area, although there are not many empty stations in this general area. The higher conductance region indicates higher intensity of conductance and trends in a similar northwest-southeast direction toward A-3 well as the trend of the shallow conductor. The observed resistivity trends parallel to the northwest-southeast oriented south and north Ertankian invert faults, which probably act as pathways of the outflow of the system. Several cross-sections were constructed to illustrate the subsurface distribution of the clay cap at Ertankian to determine the possible aerial extent of the prospect. However, due to limited time, I will only show one example of the cross-section. The Ertankian -2 profile, which passes along the Beta hot springs and extends through the Ertankian fumarole towards the southeast, shows a continuous semi-flat conductor that extends from Ertankian to the northwest and possibly delineating the outflow of the hydrothermal system. The extension of the clay cap towards the southeast is unconstrained because of the lack of empty stations. Because of the distant station shows weak conductance. This slide shows the initial conceptual model of the Ertankian area. So the integration of geology, geochemistry, and geophysics data are used to develop the conceptual model of the Ertankian prospect. From the data that integrated, the interpretation is that the invert upflow located beneath Ertankian fumarole and outflow towards to the northwest to the beta hot spring here. Prominent northwest-southeast invert faults appear to control the permeability and outflow location, as indicated also by base of low resistivity, which is shallowing to the east and distributed to the northwest-southeast trending, follow north and south Ertankian invert faults. This would be my last slide. So the conclusion from this study is that the integration of geology, geochemistry, and geophysics data indicate that geothermal potential significance may exist in the Ertankian area. The invert upflow located beneath Ertankian fumarole and outflow is interpreted to the northwest in the beta hot spring. Numerous superheated and boiling steam fans exist in this vigorous fumarolic area with some sulfur deposit. The fumaroles are typically high gas and high H2S with no indication of excess chloride from its steam condensate. However, the data shows that there is indication of geothermal fluid with magmatic input. Prominent northwest-southeast invert faults appear to control the outflow location, as indicated also by base of low resistivity, which is shallowing to the east and distributed to northwest-southeast trending, follow north and south Ertankian invert faults. Lower conductance value and deepening of clay cap base to the southwest direction indicates lower possibility of connection to Salak reservoir system. In view of the fact that phreatic explosions have occurred in the last 50 years, a detailed study of potential hazard should also precede any major development. So that's all for my presentation. Thank you. I appreciate for any feedback and comments.
Geothermal energy is a relatively environmentally friendly source of energy. It is derived from the heat of the earth. In recent years, the market for geothermal power has increased sharply, especially in emerging markets due to the economic growth due to the growing number of communities in low-income rural areas that have access to the power grid. Any governments are also increasing focus to reduce the dependency on expensive fossil fuels and not environmentally friendly. Systraco Group is a company engaged in the energy sector. Established in 1995, Systraco Group is currently very focused to be able to develop and serve you in various needs related to the geothermal sector, which among of them are hole cleaning services. Systraco Group provides comprehensive conventional fishing tools and systems include packer milling and retrieving, internal and external cutting, internal and external engagement, washover, basically every fishing application. Regardless of what's in your well, hence we've removed it successfully. We also provide a radial cutting torch that is safe and without any explosives or harmful chemical elements that can cut the tubular drilling equipment left in the well. As well, biochemical that can scale control, corrosion control, cooling water treatment and also as a rig washer. Downhole camera. Leveraging the advancement of technology today, Systraco Group also provides high-resolution downhole camera equipment and clear image quality and capable of operating up to a depth of 2,000 meters, adding to our line of services to focus on the development of the geothermal sector. Geothermal well testing. Energy Megapersada as the sister company of Systraco Group also provides the services of geothermal well testing, real-time well monitoring, geoscience. Digital remote sensing used Sniffer 4D drone. Digital remote sensing system has an advanced capability to detect and map for the following energy sector applications: steam surface breakout monitoring, well reliability and integrity monitoring, air quality mapping, well surveillance and inactive well management, geothermal associated gases detector and mapping. All of which are focused to support activities in the geothermal sector. Please, do not hesitate to contact us when you need our support, because we are there for our common progress. Thank you very much.
Good day, everyone. My name is Muara. Today, I would like to present my paper that entitled Geology Controlling Factors of the Top of Reservoir Muara Laboh Geothermal System Case Studies. This is the presentation outline. Muara Laboh Geothermal System is located about 135 kilometers southeast Padang. The company started to explore since 2008, and in 2019 we are successfully conduct COD with a maximum net capacity of 85 megawatt electric power plant. We also operate in South Sumatra with Supreme Energy Rantau Dadap that's currently in power plant construction process. The last field that we operate is in Lampung, is called Supreme Energy Raja Basa, which currently still conducting exploration. This is the geology of Muara Laboh Geothermal System. The system is located in the Great Sumatran Fault step over between Suliti segment, Siluak segment, creating a pull-apart basin. The system is closely related with Mount Patah 9 volcanism. The oldest volcanism is Mount Bangko, and it becomes younger toward southeast to the youngest volcanism in Mount Kerinci. The structure within the system is trending northwest-southeast, following the Great Sumatran trend, and we will see the alignment of the manifestation following similar trend. From surface mapping and well data, we also observe the north-south trending and the northeast-southwest trending fault that become our permeable structures. We also observe in the northeast part an outcrop of basement rock, the Barisan formation, and the pre-tertiary intrusive that may act as our system basement and boundary toward east. In terms of top of reservoir in geothermal system, the top of reservoir bounded the reservoir system section in beneath, and the non-reservoir sections above it. The definition is quite varies depending on the development stage. During exploration, we conduct a conceptual model to predict the top of reservoir, and after drilling exploration well, we refine it, and after having the completion test, that we also refine the top of reservoir definition based on temperature data. So every company have its own definitions on the temperature target that needed and the permeability indicators that being used. In terms of the objective is we want to set our production casing quite close to the top of reservoir to maximize the productivity of the well, because we don't want to set it too shallow, that may harm us with a cooler influx, or too deep, so we are puncturing the reservoir where the cementing operation will be difficult. So in Muara Laboh, we use the same process. We monitor the rock, the alteration, and the first occurrence of epidot as our indicator. We also observe whenever our MEB is dropping to below 10 and 5, we are getting closer to the top of reservoir. We see that whenever we have a MWD temperature reaching 55, more than 55, and the delta T of the temperature is more than 6 degrees, we are getting closer to the top of reservoir. We have an objective to set PCS about 30 to 50 meters above the top of reservoir. After well completion, this data will be refined by PT data. Our temperature target for this field is higher than 230 degrees C with convective temperature profile. This is the northeast sector. So in general, the production sector is divided into two. The northeast sector, where the steam cap wells located, the top of reservoir is relatively shallow. We use all the data, the geology, the wire and log data, the XRMI log, the image log. We also see the textural and also the thin section XRD data. So in the northeast sector, represented by IA3, the top of reservoir is around 650 meter depth. We set the PCS about 631 meter. So it's around 20 meter to 19 meters gap from the PCS to the top of reservoir, which is relatively good. The top of reservoir itself sits in the lower part of Patah 9 unit, and we see that our major entries are located in the different undifferentiated silicic formation. It's kind of composed of rhyolitic to dacitic silicic volcanic. We also see a change of alteration. The MEB is kind of getting lower than 10 since 621, getting closer to the top of reservoir. The top of reservoir itself located in the transition alteration zone that consists of mixed layer clay, smectite composition with chloride. We also observe that in the area, the major vein species is composed of calcite and quartz. This is the thin section of the lower Patah 9 underside. This kind of showing a lava-like underside with a chloride and quartz vein. We also see a vein in MLA2 in the northeast sector, composed of calcite, wyrachite, and anhydrite. This is anhydrite and wyrachite. From the image log, we see that near to the top of reservoir, we see some kind of brecciated, possibly a contact between more massive lava like rock interval in the above part and relatively layered interval beneath it. So we move on the southwest sector, the top of reservoir. is located in the deeper level, is around 300-meter elevation. We site the PCF at around 990 meters. It's relatively quite far from our expected top of reservoir. The top of reservoir itself located within the intercalated andesite and dacite unit. We also observe similar lithological sequence in the shallow level, but no permeability occur at this particular section. We see the vein characteristic proximate to the top of reservoir location is composed of calcite sericite vein that cross-cut the early epidote vein within this area. And after conducting the study, we see that the late epidote vein is being encapsulated or cross-cut by calcite and anhydrite, meaning that it's possibly that in the past time it encounters a boiling process. So continuing to the thin section of the intercalated andesite and dacitic interval, this is a porphyritic dacite. We see kind of being altered with silica and chloride. In terms of vein characteristic in the shallow part near the top of reservoir, we see that the epidote vein is being covered or encapsulated by quartz and calcite. Compared to near to the pit zone, we see a epidote vein that has that occurs in the open space that still have major permeability with some calcite occurrence after the epidote vein. So comparing all the data between the northeast well, A3, A2, and H1, and the southwest sector wells, H4 and H2, as we can see that the southwest sector have similar lithological sequence like the northeast sector, but the permeability in the shallow part is being blocked by later calcite and anhydrite mineral that potentially block the distribution of the shallow reservoir in this part. And after getting closer to the top of reservoir, the permeability seems to improve, and we also see that the vein still showing intergrowth of epidote, a lot of open space. Tim Stimek in his paper suggests that the observation is caused by a rapid boiling process in the later episode that block all the permeability within the shallow area that makes the interval is not that permeable. Looking at the cross sections on the northeast sector in the north and the southwest sector in the southwest, we can see that the top of reservoir is shallower in the north and become more deeper in the south. We can see that the top of reservoir in the northeast is composed of transition alteration zone because of the deposition of calcite. The permeability is not continuous toward the southwest sector in the shallow part section, but still the permeability in the propylitic alteration still develop and we still have a good permeability in this part of the area. So, as a summary, top of reservoir definition is varies between operators and stage of project development. We see that the Northeast Southwest sector, top of reservoir, is shallower, located within the Patah Sembilan underside, close to the contact, and we see that the observation is a transition alteration. We see that in Southwest sector, we found a similar shallow stratigraphy like the Northeast sector, but not much permeability. It's located in the intercalage dacite and andesite unit with profilytic alteration. In terms of vein, the Northeast sector have a calcite quartzite as a dominant vein species, possibly related with the steam cap existence, and more epidote, calcite quartz, and saricite in the Southwest sector, kind of suggesting that this is, and confirming this is still a liquid-dominated productive zone. In terms of the reason why that the Southwest sector is more deeper, have a deeper top of reservoir, is possibly the permeability destruction due to calcite and anhydrite deposition. The interpretation is the rapid bailing process due to the sector collapse that deposit or back the deposition process is very intensive in the shallow Southwest sector. That's all my presentation. Thank you, and we'll be glad to see our discussion. Thank you very much.
Indonesia merupakan salah satu negara yang memiliki potensi energi panas bumi terbesar di dunia. Saat ini, Indonesia menduduki peringkat 2 dunia sebagai negara penghasil listrik dari energi panas bumi. Selain sebagai energi yang bersih dan berkelanjutan, peran energi panas bumi sebagai baseload penyediaan listrik menjadi pertimbangan utama agar pengembangannya diprioritaskan. Oleh karena itu, dalam menjaga ketahanan energi suatu negara, energi panas bumi dapat menjadi andalan untuk memasok listrik guna memenuhi target bauran energi 23% EBT di tahun 2025, sesuai dengan amanat dari Kebijakan Energi Nasional. Untuk memenuhi pencapaian target EBT, dalam bauran energi tersebut, Indonesia layak melakukan percepatan pembangunan proyek PLTP di Indonesia. PT Geodipa Energi Persero adalah perusahaan yang bergerak di bidang energi panas bumi mulai dari eksplorasi hingga eksploitasi. Perusahaan didirikan pada tanggal 5 Juli tahun 2002. Kemudian pada tahun 2011, melalui Peraturan Pemerintah Nomor 62 Tahun 2011, Geodipa ditetapkan sebagai Persero yang pengawasan dan pembinaannya berada di bawah Kementerian Keuangan dan PT PLN Persero, yang juga merupakan salah satu Special Mission Vehicle atau SMV di bawah Kementerian Keuangan dengan misi mendukung program pemerintah dalam penyediaan listrik tenaga panas bumi yang aman dan ramah lingkungan, serta memberikan manfaat besar kepada Indonesia. Geodipa siap untuk melanjutkan pengembangan proyek PLTP Dieng Patuha yang masuk dalam Fast Track Program atau FTP, tahap 2 10.000 MW. Bagian dari program 35.000 MW yang merupakan program pemerintah di bidang pembangunan infrastruktur ketenagalistrikan.
Good afternoon, everyone. My name is Sigit Suryanto. Today, I am going to give a presentation for our research with the title Integrated Geoscience Data to Identify Heat Source Beneath Ume Volcanic Complex in Tompaso Geothermal Field, Indonesia. This paper was written by me as author, and co-author are Pak Tovan Sastranegara, Pak Antonius Risanguntoro, Pak Nanda Naji, Pak Ristio Effendi, Pak Imam Baru Raharjo, and Ibu Suryantini. In this paper, I will explain how to determine the location of the heat source based on the geological data, geophysical data like resistivity from MT and gravity, geochemistry data from the isotope like deuterium and oxygen 18, and pressure and temperature from the borehole. Heat source is very important in a geothermal system because the heat source always support heat to the fluid in geothermal reservoir. The location of the heat source is very important to know because common related to the main outflow zone or main prospect zone in a geothermal system. Outline from this presentation is divided to 7 parts. Number 1 is background, number 2 location, number 3 geological map, number 4 resistivity and gravity, number 5 isotope, deuterium and oxygen 18, number 6 pressure and temperature from the borehole, number 7 conclusion. This is the background from this research. The location of the heat source is very important to know. An approach, geologic setting, remote sensing, resistivity and gravity, isotope, and temperature measurement from the wells can predict the location of a heat source. This method can be used to make sure the location of the heat source, especially in Tompasso geothermal field. The purpose of this research to support update conceptual model of Tompasso geothermal field. The Tompasso geothermal field is located in Tompasso District, Minahasa Regency, North Sulawesi Province, Indonesia. Tompasso geothermal field is apart from Lahendong working area or 30 km southern part from Lahendong geothermal field. Lahendong geothermal field around here. Geologic setting from the Tompasso geothermal area is related to the caldera system. The youngest volcanism rise up in the caldera wall. In this map, we can see the Monsoputan. Monsoputan is the recent volcanism related to the recent subduction zone in the Molucca Sea or in the eastern part from the Tompasso geothermal field. Around the Monsoputan, we call the Sempu volcanic complex around here was interpreted as the main heat source of Tompasso geothermal field. This is a geological map from the Tompasso geothermal field. In the southwest area, we can see the Monsoputan, and this is the Sempu volcanic complex, and this is the main focus area in this research we call the Umeh volcanic complex. The remote sensing data shows that some lineament like structural geology, Toraget-Totolan fault, Soputan fault, and others geological features. In this map, we can see the circular feature in the top of Mount Umeh. Circular feature is usually related to the center of the volcanism, and the yellow one is Umeh volcanic complex. Umeh volcanic complex was interpreted like monogenetic volcanism, which rise up among the Tondano explosive product, the pink one. There are several manifestations around the Umeh volcanic complex. We will discuss later in the next slide. This is the resistivity and gravity data section from the southwest to the northeast. Based on the resistivity data, we can see the updoming pattern beneath Umeh volcanic complex. And if we compare to the gravity data, there is a high gravity anomaly. High gravity anomaly common related to the intrusion body or rock has high gravity value. Present updoming pattern and high gravity anomaly in the same location beneath Umeh volcanic complex. It's make possible in this location has additional heat source. This is graph from Gegenbach 1992 showing the ratio between oxygen-18 and deuterium. These isotope data were taken from the geothermal manifestation in Tompasu geothermal field. We can see plot the TPS1 and TPS8 shifting to the magmatic zone. The location of the TPS1 and TPS8 around the Umeh volcanic complex. It means the location TPS1 and TPS8 near from the heat source. This is a pressure and temperature data from the borehole. The well that is directed just below the UFC, LSDA, around here, show a higher temperature than production well in LSDB, around here. The temperature in LSDA reaches until 300 degrees C, and LSDA has thick convective zone like this. Compared to the temperature in the LSDB, the temperature LSDB around the 250 until 275, and at the deeper, we can see like reversal pattern like this. The location of the LSDA farther from the main heat source is Sempu compared to the location of LSDB around here. But the temperature from LSDA higher than the temperature in LSDB. It means the location of LSDA possible has near from additional heat source. This is the conclusion for our research. The heat source beneath Umeh volcanic complex can identify the one circular feature on the top of Mount Umeh that looks like a small crater in remote sensing data. So it's possible that location beneath Umeh volcanic complex has additional heat source. And number two, the content of deuterium and oxygen-18 from the manifestation on UFC, TPS1 and TPS8 shifting to the magmatic zone. And number three, present updoming pattern in resistivity and high anomaly gravity in the beneath Umeh volcanic complex. It means the location, this location possible has additional heat source. And based on the temperature from LSDA higher than the temperature in the temperature in LSDB. The location LSDA farther from main heat source Sempu volcanic complex compared to the LSDB, but the temperature higher. This means the location of the LSDA possible near from the heat source. Thus it could be interpreted that there was a heat source under UFC, manifestation, complex. Thank you very much.
Assalamualaikum warahmatullahi wabarakatuh, and good afternoon everyone. My name is Fauzia Maswa, and I'm from Geothermal Master Student, Bandung Institute of Technology. At the moment, I will present my research paper about magnetotelluric data analysis using phase tensor and tipper strike to determine geoelectrical strike in ex-geothermal field. First, I want to explain why we have to know about this data analysis in magnetotelluric. Okay, magnetotelluric method is passive geophysical method that measure natural electromagnetic field to estimate the subsurface resistivity structure. This method is powerful in geothermal exploration because there is the relationship between the temperature effect rock formation and mineralization with the conductivity or resistivity. This method can also determine the geometry of the subsurface based on the conductivity or resistivity characteristic. But to increase understanding about the subsurface, it's developed from a comprehensive and high-quality data analysis. So, before we conducting to the empty data inversion, data analysis, including determining the geoelectrical strike direction, should be performed. It's because there is an assumption should be fulfilled. The empty data have to be rotated to the geoelectrical strike direction before we perform to the empty data inversion. As shown in this figure, this is a simple 2D model with a vertical contact generated by Simpson and Barr 2005. In 2D earth structure, the resistivity changes in depth and one of the horizontal direction, X or Y. And as we can see in this model, the resistivity changed in a Y direction and separated by the vertical contact. The constant resistivity of the other direction, I mean the X direction, are called the geoelectrical strike. And therefore, in 2D empty data inversion, the electromagnetic field can be decoupled into two independent modes by rotating the empty data to the geoelectrical strike. It is E-polarization and B-polarization. E-polarization, when the electrical field is parallel to the strike, and bipolarization when the electrical field is perpendicular to the strike. So first, we have to obtain or to determine the geoelectrical strike direction before we perform to the empty data inversion. And we use phase tensor and TOR strike parameters to identify the geoelectrical strike in the subsurface. Okay, proceed to the next slide. Okay, the electrical field and magnetic field from the MT measurement are used to calculate the impedance, and the ratio of the real and imaginary part of the impedance are called phase tensor, and it contains the information of the geoelectrical strike direction in subsurface. Since the phase tensor contains the 90-degree ambiguity, we use TOR strike to resolve it, and it is calculated from the vertical component of magnetic field and generated by a linear combination of horizontal magnetic field. Okay, proceed to the next slide. This is the geological structure map of the area, and as we can see, it shows the complexity structure in the surface. The geological structure developed in the area are dominated by north-south, northwest-southeast trend, and northeast-southwest trend. This information of the geological structure is used to confirm the result of the magnetotelluric analysis. I mean, TOR strike and phase tensor. Okay, proceed to the next slide. We applied 25 empty sites to investigate the geoelectrical strike of the area, and the distance between the sites varies between 500 until 1,000 meters. Okay, we analyze the phase tensor and TOR strike formulated in Python, and the result of phase tensor and TOR strike are plotted to a Ross diagram to know the dominant geoelectrical strike of the area. And we use the information from the geological structure to confirm the result from the phase tensor and TOR strike. And as we can see, the result from phase tensor and TOR strike show the consistency of the geoelectrical strike in northeast southwest direction, and confirm with the geological information, I mean the geological structure of the area. We found that the dominant geoelectrical strike is estimated at north 15 degrees east, and the result shows a good correspond with the northeast southwest trend regional structure of the area. Okay, proceed to the next slide. We also identify the dimensionality of magnetotelluric data from 14 empty sites, and we use Q angle parameters from phase tensor. The result shows the majority of magnetotelluric data in short period, I mean in the shallow part, suggesting evident 1D or 2D structures, and it characterized by the low of the skew value, as we can see in the light color. And meanwhile, the long periods or the deeper part, the empty data show the 3D structures, and it characterized by the large of the skew value, as we can see in the dark color. And we found that the deeper part of the area, it indicates the complexity of the structure in subsurface. we identify the dimensionality of magnetotelluric data to better understand about the subsurface characteristic. And from the analysis, we conclude that the result shows 1D or 2D structure of the magnetotelluric data in short periods. Meanwhile, the long periods, majority of the magnetotelluric data show 3D structure. We also found that the dominant geoelectrical strike is around north of 15 degrees east, and it is confirmed with the regional structure of the area. And last but not least, I would say my highest appreciation for PT Geodipa Energi Persero, which supported and provided the magnetotelluric data, and the authors benefit fruitful discussion with Mas Angga from Geothermal Master Program, Kak Desi, Kak Anggi, and Mas Pesta from Earth Physics Department. The authors will also like gratitude to Modeling and Inversion Laboratory and Geothermal Laboratory. Thank you very much.
Hello participant of ITB International Geothermal Workshop. Let me introduce myself. My name is Betsebes Barani from Geothermal Master Program of ITB. On behalf of other co-authors, I will present about our research. Our research is about geological control on thermal manifestation occurrences in Batu Gede and Batu Kapur based on the result of a preliminary survey. This is the outline of my presentation. I will start with introduction, data and method, tectonic setting, and regional geology, and then discussion including geology and geochemistry, and close with conclusion. This map is showing the location of research area. Batu Kapur and Batu Gede are two areas located in Subang Regency, West Java Province, around 13 to 15 km from the northern part of Tangkuban Perahu volcano. These two areas are 5 km away, which is not too far. In general, manifestation in these two areas are generally characterized by the presence of bicarbonate warm springs with a natural pH. Despite the similar characteristic of their manifestation, there is a significant characteristic difference between them. Acidic pH cold spring with pungent smell of sulfur with mud pool and acid alteration emerge in the Batu Gede area. What is the cause? What is the geological control? Geological control like permeability, host rock, and heat source will affect the emergence and also characteristic of the manifestations. In this research area, as a preliminary, we focus more on permeability that act as the controller of the occurrence of manifestations. Permeability consists of primary permeability and secondary permeability. We will confirm which permeability control the occurrence of manifestation in both areas. Based on that background, this research is aimed to determine the control of geothermal manifestations at Batu Gede and Batu Kapur area by conducting preliminary geological study with additional geochemical data from anomaly manifestation. Data that we use are from literature and field data. Literature data consists of regional geology, tectonic setting, and water geochemistry, and field data consists of outcrop including lithology and structure, and geochemistry of manifestations. Petrography analysis is also conducted to confirm the lithology, while geochemistry of manifestation is collected from acid cold spring sample. To understand the occurrences of Batu Gede and Batu Kapur geothermal manifestations, geological mapping has been conducted. The basic framework is to comprehend the correlation of the occurrence of manifestation with drainage pattern, slope, and catchment area, lithology, whether the manifestation only emerged in a certain lithology or in a lithological contact, geological structure, to find structure evident along manifestation, to see manifestation discharge. If the flow rate is high, manifestation would be highly influenced by structure. Its own distribution and characteristics such as dimension, bubbling distribution, and alteration. Geochemistry analysis on manifestation is also been done, with warm spring manifestation is referenced from Faururosi et al. 2015 and cation-anion analysis on cold spring manifestation water sample. Java is located at the southern part of the Sundaland of Eurasian Plate, where the Indian-Australian Plate is subducted beneath Eurasian Plate. West Java is considered to be located in the transitional zone between oblique subduction in Sumatra and orthogonal subduction at the eastern part of West Java. Regional lithological units that present in the study area from older to younger respectively are Kaliwangu Formation, Citalang Formation, older volcanic product pumiceous tuff, old volcanic product lava, and alluvium. In the southern part of the study area, less old volcanic product lava, pumiceous tuff, and older volcanic products. Undifferentiated young volcanic products found in the middle area. These are eruption products of Tangkuban Perahu volcano located in the south of the study area. The northward area is dominated by Citalang and Kaliwangu Formation. Kaliwangu Formation is indicated as marine sediment corresponding with the presence of calcareous sandstone and limestone. Kaliwangu Formation has regional dipping direction southward approximately 10 until 29 degrees. It can be interpreted as proof that Kaliwangu Formation can be found below the study area. Kaliwangu Formation's bed is relatively thick on east, thinner on the middle area and getting thicker eastward. This condition causes the occurrence of travertine on Batu Kapur is more than Batu Gede. Remote sensing geomorphology is one of the important things to observe the control of the occurrence of manifestation. This is part of the pre-field work. What we will observe here is the drainage pattern, slope, and catchment area. From these three analyses, we will briefly discuss matters that relate directly to the control of manifestation. Following is the drainage pattern map of Batu Gede and Batu Kapur. In summary, both areas are dominated by a rectangular pattern as an indicative of streams following prominent fault or joint system. At Batu Gede, particularly around manifestations, there is a significant change of the slope, where the gently area is surrounded by steep area. It might indicate the presence of fault or lithological contact. Manifestation emerge in gentle slope, therefore it might be associated with fine-grained size rock or basin or graben. Meanwhile, Batu Kapur is included in the relatively steep hills unit. It seems to be associated with fault structure that were inferred from topographical offsets, river alignments, and steep slope alignments. Origin of the catchment area is from the flank of Tangkuban Perahu in the northern part of research area. It indicates that the regional flow is still getting effect from Tangkuban Perahu. However, from detailed observation, Batu Gede's manifestation in reality is not directly affected by Tangkuban Perahu. The flow direction of Tangkuban Perahu product is obstructed by a ridge that becomes the boundary of Batu Gede's subcatchment. The manifestation is concentrated in the main valley of the subcatchment. Flow direction is originated from a narrow ridge. These facts indicated that Batu Gede is structural control manifestation. Meanwhile, Batu Kapur manifestation flow clearly originates from ridge lineament with trend northwest-southeast and west-northwest east-southeast. This shows that batu kapur is correlated with heat flow with a source from a certain depth. Lithology can also control the occurrence of manifestations. In this section, we will discuss about the key findings that can significantly affect the occurrence of manifestation at both areas. Based on field mapping, lithology in the research area mostly consists of volcanic rock like andesite, basalt lava, crystal tuff, pumice-rich pyroclastic breccia, vitric tuff, lapilli tuff, volcanic classic, and sedimentary rock such as claystone, sandstone, and limestone. From this geological map, we can see that these two manifestation clusters are located in the transition environment between volcanic product of Tangkuban Perahu and sedimentary rock that indicated with the presence of volcanic clastic and unmappable limestone. For more detail, we will discuss the evidence that found in the field. Lithological contact between pumice-rich pyroclastic breccia and lapilli tuff is found near two acid cold spring manifestation of Batu Gede. This contact is thought to become the control of alteration that is affected by water table. Pumice-rich breccia is tending to the northwestern part, while lapilli tuff is thickening. Mud pool and low pH cold spring might be controlled by lithological contact and current water table. Mud is easier to form, especially in fine-grained sized rocks. Pumice-rich breccia contact with volcanic clastic was observed near Batu Kapur, where volcanic clastic is exposed in the lower part. There is charcoal layer between the contact. This contact can be assumed as a permeable zone. The occurrence of volcanic clastic became an indication that this area is part of a distal facies. The appearance of volcanic clastic is also supported by the presence of piszoid texture. This shows that research area is in the transition environment where volcanic rock meets the sedimentary product. This becomes a contact that can be a permeable zone. The presence of this rock is also indicated that at greater depth, host rock of reservoir might be controlled by marine sedimentary rock, which is Kaliwangu Formation. Similar with Batu Gede, contact of ignimbrite and volcanic clastic was also found at Batu Kapur. However, volcanic clastic at Batu Kapur is found at the lower elevation, covered by very thick ignimbrite product. Around Batu Kapur manifestation, spotted limestone containing mollusca was also exposed. This rock is thought to originate from Kaliwangu Formation, which is a marine sedimentary formation formed in shallow marine. By looking at the evidence of Kaliwangu Formation presence, volcanic clastic as well as the very thick ignimbrite product, the area around Batu Kapur might be associated with sedimentary basin. This should be confirmed by conducting further study such as geophysical survey. Aside from lithology, fault also has an important role in controlling the occurrence of manifestation. Fault is interpreted controlling the manifestation when evidence of fault are found in the vicinity of research area, especially around the manifestation. Following are the evidence of fault that was observed in the field. Following is geological structure map of the study area. We can see that the Batu Gede area is cut by sinistral strike slip fault that results in overstep structure around the manifestation, while Batu Kapur area is cut by relatively north-south and west-northwest east-southeast direction fault. For more detail, we will look at evidence found in the field. Overstepping structure in the Batu Gede area is also supported by the appearance of its morphology, where manifestations are in the flat morphology flanked by steep morphology. Following is the example of overstepping structure that was observed in the field. This is also supported by petrographic analysis that shows overstepping structure in thin section. Following are the evidence of structure that was found along the Batu Kapur River consists of silicon site, fault plane, and offset showing the sinistral strike slip fault. This fault is interpreted as antithetic fault that cut fault with north-northwest south-southeast direction. The last thing to be discussed is the distribution and characteristic of manifestations found in the field. In this section, we will look to what extent the distribution of manifestation in the study area. At Batu Kapur area, thermal springs and abundance of travertine are found along the river. This slide shows the characteristic manifestation dominated by relatively warm spring with neutral pH and high flow rate. High flow rate shows the indication of fault. At some areas, there is warm spring that emerge from lithological contact. that lithological contact is thought to be not too dominant permeable zone in the research area. The emergence of travertine and intense bubbling indicate that reservoir in the subsurface is controlled by rock from Kaliwang Formation. From this sketch, we can see that manifestation around Batu Kapur is controlled by the intersection of north-northwest, south-southeast, and west-northwest, east-southeast strike slip fault and lithological contact. Furthermore, we will discuss manifestation in Batu Gede. This map showing manifestation with relatively warm temperature, neutral pH, and high flow rate. However, there is anomalous manifestation that occur in the surface in the form of mud pool and acid cold spring. Following is the distribution of alteration and bubble in the Batu Gede area, where the distribution is only centered on the stepping structure, as shown in the sketch. Following is the appearance of mud pool with a dimension of 40 x 70 cm. There is acid alteration with the presence of sulfur and pungent odor smell around it. Next, we would discuss about geochemistry of Batu Gede and Batu Kapur. Warm spring geochemical data, a reference from Farrozi et al. 2015, while cold spring geochemical data are primary data. The high content of chloride is also followed by the contents of sodium and bicarbonate. This is thought to be related to the formation of marine sediments beneath the surface from Kaliwang Formation. Meanwhile, acid cold spring manifestation in Batu Gede contain high concentration of sulfate. This could be related to condensation the hydrogen sulfide underground, indicating the possibility of subsurface magmatic activity. Conclusion of this research are, both of Batu Gede and Batu Kapur area are dominantly controlled by secondary permeability. Batu Gede manifestation is controlled by overstepping structure, meanwhile, Batu Kapur manifestation is by intersection fault. Based on a high sulfate content, appearance of acid alteration and sulfur, acidic cold spring in Batu Gede might be associated with magmatic activity beneath the surface. The last is to confirm the subsurface magmatic activity. Further research such as gravity and gas geochemistry analysis need to be done. This is the end of my presentation. Thank you for your attention.
PT Kogindo Daya Bersama adalah perusahaan ketenagalistrikan di Indonesia yang beroperasi di seluruh wilayah Indonesia dari Sabang sampai Merauke. Kogindo didirikan pada tahun 1998 sebagai anak perusahaan PT Indonesia Power dan bagian dari PT PLN Persero. Kogindo memiliki 4 bidang usaha, yaitu suplai energi, jasa operasi dan pemeliharaan pembangkit listrik, jasa gas dan diesel engine, dan jasa maintenance, repair, overhaul, MRO. Dalam kurun waktu lebih dari 2 dekade, kami telah mengembangkan bisnis kami secara signifikan dan membangun dasar yang kokoh bagi portofolio perusahaan di level nasional maupun internasional. Kogindo menawarkan satu solusi layanan terintegrasi di bidang ketenaga listrikan melalui Kogindo Integrated Solution. Dengan menggabungkan kompetensi, teknologi dan pengalaman, kami yakin dapat membantu para pelanggan mencapai efisiensi dan keandalan pengoperasian pembangkit listrik di Indonesia dan seluruh belahan dunia. Kogindo, trusted partner for power generation.
Hello everyone. Well, today I'm going to explain a little bit about black material deposition in surface facilities during commissioning in Muara Laboh Geothermal. This is going to be a short presentation because it's not going to be complex or sophisticated. I'm not going to go into detail. I'm not going to explain anything about thermodynamic, the dynamic of the fluid itself, but I'm more into getting people to be aware of the black material occurrence during the commissioning program, and how was it formed based on our analysis using the SEM and EDX. So this is me, Gilman Azka, field chemist from Supplementary Laboh, and Alfiadi as order, and as a geochemist, and Herwin Aziz as a chief development geologist, and Aulia as a geochemist as well. Let's just get on to the presentation then. This is the outline of the presentation. I'm gonna have a little bit not discussion, I'm gonna explain a little bit about the geothermal power plant and more of an overview. And then the problem prior to COD. Prior to COD, we have this pre-COD program, such as pre-commissioning and commissioning. And then during the pre-COD program, we have this problem, big issue back then, black material appearance in steam above ground system. Then we took the sample, and I'm going to show you the result based on SEM EDX. For that, we're going to deduct the probable source of the black material and a little bit of summary. I'm not going to put any conclusion there because I haven't put any point out objective, so it's better to put the summary. For me, it's just a matter of principle. If there is no objective, then there will be no conclusion within the paper. So this is the first geothermal power plant that has been operational for about 6 months, 6 to 7 months till July. And in West Sumatra, located in Solok Regency, I didn't put any map there because it's quite easy to find. If you search it, Google, you put Solok name there, you're gonna find the regency, and you type another word such as geothermal power plant, you're gonna find the location is quite easy to find. And then we accomplished commissioning operation date on 16 December 2019. It's been operational for 7 months till July 2020. The generation itself, well, 80 to 85 megawatt electricity net, depends on PL and demand. So maximum 85 megawatt. So prior to COD, the plant underwent several major steps such as pre-commissioning and commissioning program. We call this a pre-COD program. So the pre-COD program also consists of steam blow, step 1 to step 3, and then also the pre-commissioning, we check all the parameter and also the electrical sort of stuff, and the commissioning, including the RR test work. And then we did a generation for about 1 month, see how it went. It went quite well, despite the fact that we encountered some problem, such as black material appearance. The other problem also, error reading, not really a big issue, but this one, it was a big issue back then. And this is the power plant overview. So we have a HP line, high pressure line, and LP or low pressure line. The HP dedicated for a HP well or high pressure well separated on their own. HP separator goes into HP section of the turbine. On the other hand, LP separator, the fluid comes from the flash brine of the HP fluid, and then also mix with the LP, the LP source of from the well. So mix together, get into the LP separator, and then goes into the same turbine as the HP steam. So HP and LP go into the same turbine. And the rest is quite similar to the other conservative geothermal system. We have this condenser, direct contact, and the cooling tower circled back to the condenser. And some of the steam condensate will be injected back to the reservoir. We have this condensate injection well. It differs with the brine injection well. So this is a hot brine injection well. And then during the commissioning program, we encountered some black material, such as beneath the HP separator drain, and then the LP separator, and then the CDP or condensate drain pot, and HP scrubber drain, and also HP strainer turbine. Also, surprisingly, we also encountered the black material within the cooling tower basin. It was quite surprising because could have been damaged the turbine, so it went through the turbine and could probably damage the turbine itself. Wait a minute. I gotta turn off the video. It's quite noisy. There we go. So where was I? So the black material actually went through the turbine and went to the cooling tower. So the real question is, how was the turbine condition when the black material went through the turbine? So plenty of location for the black material itself. We encountered plenty of location, but I only show you some of the result from the HP separator and the HP scanner. We're going to see how different it is for both of them. This is the physical appearance from the condensate drain pot. As you can see, it is really very grain, very fine grain, blackish and reddish, probably some rust in it, or it is really rust. And then this is from the strainer of the turbine. It has magnetic property. And this is the thermal pond. Thermal pond actually from the condensate mostly. So from the CDP, they go to the AFT of the condensate, go to the thermal pond. As you can see here, the water from blue turned into black, some part of it. And this one, it's in the cooling tower basin, turned into completely black. So we have to shut down during the commissioning program because of the clogging at the turbine strainer, and we have to wash all of it. The fact that it was black. And then some sample taken to ITB to be analyzed with SEM EX. This is the result from the HP, and this is the result from the turbine strainer. You can see some difference there. First, the HP separator got silica, arsen, and calcium peak. Meanwhile, on the result for the turbine strainer, it doesn't show us any calcium, silica, or arsen. The silica and arsen and also calcium could have been a product of debris from the well itself, but it has been separated beneath the separator. While the turbine strainer, the sample from the turbine strainer, it shows us consistent of a peak of iron and also sulfur. I still don't know why gold is also present there, but I still don't have the answer for that. Coating, I'm not sure why there is gold peak there. So mostly the EDX result consists of iron and sulfur and also oxygen. And if we kind of have this kind of X-ray, we will see it was pure iron sulfide, dominantly iron sulfide. This and we go into the probable source of the black material. You can see here that the black material stays beneath the bottle. So the density of the black material is bigger than the steam condensate. This is condensate from HB separator. And this is the picture of a brine. It's a clear image. I'm gonna zoom in a little bit. Yes, you can see the brine. It is really clear. It contains no black material. So the source is not going to be from the reservoir. So two remaining source, casing or surface related. Surface related means the pipe. And then also, if any theory tell us that it's from the reservoir, no, because we also conducted a flowing test for 2 years, and the very fine grain of material never been encountered. So, if it is from the casing, the brine won't be clear as this kind of sample. This was taken during the RR test, reliability run test, on I think in December 2019. It's clear. So the most probable source of the black material itself, it's from the surface related source. It's from the pipe. And how it was formed? It was formed due to the reaction between condensate contains some amount of hydrogen sulfide and oxygen. The inner pipe actually reacted with the remaining gases, and it produced the black material. The black material contains iron sulfide of pyrite, and it's likely to happen that way. And also shows the difference between the strainer and also the HB separator sample. So it's not from the reservoir, not from the casing. The casing is okay. Probably the remaining rust reacted with the gases. And this is the last page of the presentation. This is a summary. We've been operational for about 7 months with the capacity of 80 to 85 megawatt electricity. And prior to COD, black material encountered within this location, CGP thermal plant cooling tower basin. Based on the analysis result, it was mostly iron sulfide or pyrite. And the reaction between inner pipe and also the condensate created that material. There are also 2 questions left, cannot be answered now because period of black material occurrence. It means that when we have the shut-in program and then get the well back online after 2 weeks, 4 weeks, or a month, will the black material occur once more? That's the question we cannot answer right now. We have to see. And then the current black condition after the black material went through the turbine, went to the cooling tower basin. I think that will be all my presentation. And thank you for your attention, and thank you for Supreme as well for giving me this kind of opportunity to present data.
Geothermal energy is a relatively environmentally friendly source of energy. It is derived from the heat of the earth. In recent years, the market for geothermal power has increased sharply, especially in emerging markets due to the economic growth due to the growing number of communities in low-income rural areas that have access to the power grid. Many governments are also increasing focus to reduce the dependency on expensive fossil fuels and not environmentally friendly. Systraco Group is a company engaged in the energy sector. Established in 1995, Systraco Group is currently very focused to be able to develop and serve you in various needs related to the geothermal sector, which among of them are hole cleaning services. Systraco Group provides comprehensive conventional fishing tools and systems include packer milling and retrieving, internal and external cutting, internal and external engagement, washover, basically every fishing application. Regardless of what's in your well, hence we've removed it successfully. We also provide a radial cutting torch that is safe and without any explosives or harmful chemical elements that can cut the tubular drilling equipment left in the well. As well, biochemical that can scale control, corrosion control, cooling water treatment and also as a rig washer. Downhole camera. Leveraging the advancement of technology today, Systraco Group also provides high-resolution downhole camera equipment and clear image quality and capable of operating up to a depth of 2,000 meters, adding to our line of services to focus on the development of the geothermal sector. Geothermal well testing. Energy Megapersada as the sister company of Systraco Group also provides the services of geothermal well testing, real-time well monitoring, geoscience. Digital remote sensing used Sniffer 4D drone. Digital remote sensing system has an advanced capability to detect and map for the following energy sector applications: steam surface breakout monitoring, well reliability and integrity monitoring, air quality mapping, well surveillance and inactive well management, geothermal associated gases detector and mapping. All of which are focused to support activities in the geothermal sector. Please, do not hesitate to contact us when you need our support, because we are there for our common progress. Thank you very much.